Okay, so in this lesson, we're going to talk about some concepts about lighting vegetable crops. We're talking primarily about tomatoes and a little bit about peppers today. Um, so we're by now we're very familiar with what photosynthesis is and what it does. It takes sunlight and converts carbon dioxide and water into sugar, right? And as a sort of a base fact for you to remember, you need about 80 to 110 watts per square meter of light intensity for photosynthesis to happen. So if you go below that level of intensity, you end up with not much happening. Um, Now, you might say, well, then all we need is 110 watts, except with the vegetable crops, they're very tall and there's a lot of leaves, which cuts into the amount of penetration into the canopy. So typically we're looking at around 500 watts per square meters needed for optimal growth. Um, that way we know that there's light penetrating down to the lower parts of the canopy to make those leaves useful. All right. Uh, Less than 5% of the sunlight that actually hits your crop, you know, is actually used for photosynthesis. The rest of it is reflected or turned into heat. And of course, we know that plants look green because a lot of that is reflected off the plant. We'll talk more about this in another lesson about spectrums and things like that, so don't worry, that's coming. Um, you also know that you can have too much light. Remember we talked about photooxidation? So anything more than, say, 1,500 micromoles per square meter is going to risk burning your crop, damaging the leaves, or even the fruit in the case of peppers. And then, of course, we know that light also heats up things, right? And so solar radiation also contributes to evapotranspiration. That means it's warming the plant and it's removing water from the plant, causing transpiration to happen, which is a good thing. And of course, it kind of works nicely that as the sun gets higher and more powerful, the plant will respond with more transpiration. So this is sort of a mutually evolved system. Um, this graph here, just going back to what we were talking about, shows you what wavelengths are transmitted into the canopy. And green light does filter down lower into the canopy, as does far red light. Remember, far red light goes down to the bottom of the crop, causing stretch. And green light, interestingly, makes it through or bounces off leaves to get to the lower leaves. And what is interesting is that green's completely not useless because it does trigger some photosynthesis. So green light actually improves the efficiency of lower leaves, making them contributors for sugar production. So this green is an important part of a spectrum. Not hugely important, but it is useful. So there are three types of artificial lighting that we need to remember about, right? There's what we call replacement lighting. Replacement lighting is the kind of lighting you would see in an indoor chamber that has no glass. That means that all the spectrum should be replaced at appropriate intensities for the crops to grow properly. Then there's what we're kind of talking about today, which is supplemental lighting. And supplemental lighting means that, okay, so sunlight is there, but we're augmenting that with our own lights as best we can for the most efficient use of electricity. That's supplemental lighting, or sometimes called top lighting. Then there's photoperiodic lighting, which we're not going to talk about today. We will talk about photoperiod, but not photoperiod. In our other lesson for crops too, we talked about mum production and how we use regular bulbs in the middle of the night, not a huge amount of light, but enough to trick the plants into thinking that there's a different photoperiod happening. So that's a different type of lighting. So as far as supplemental lighting goes, there's uh, there's the choices you have to make as opposed to sort of when you're going to turn the lights on and for how long. Um, when you're looking at the calendar of your year, we know that the day length changes. You know, in the winter we have short days here in Canada, and in the summer we have long days, which means it's an entire continuum between the shortest day and the longest day. So when you're looking at less than 4.5 hours per day, there's definitely room for supplemental lighting. And the other thing, that not only just the length of the day, but the height of the sun in the sky has a big impact uh, on the intensity. We talked about this in the fall with climate. In the winter, the sun is so low in the sky, a lot of the light is, pushed through more atmosphere and bounces off. You almost 5% of the sunlight, useful sunlight, in compared to the summer. So that's a pretty big loss in the wintertime. So it's obviously in the times of year where we use supplemental lighting is when the sun is weakest, right? That's when it's most beneficial. So this graph is just showing us the hours of daylight for a given latitude, and we're sitting at 43 degrees north. The red line is 50 degrees north, so we're just under that. Let's say we're here. That puts it 7 hours of daylight in January. This is our January month. So there's not a lot of light in January. We just went through the winter. We know that, December and January, not much happens. I mean, we have grow lights, thank goodness, but the rest of the crops, not much happened. In terms of peak light, that also changes, because remember I talked about the angle of the sun in the atmosphere. So these shorter days, the sun's lower in the sky. So our peak power output is also lower. So let's take a look at that. So 40 degrees is between red and green. Let's say it's around here. And for January, we're looking at, 100 watts per square meter. Not a lot of power. Remember I said, with tall tomato crops, you're looking at 500 watts by the time that light trickles down to the lower leaves. So we don't have enough to drive real growth, which is why a lot of farms, don't plant their tomatoes and peppers until December. Then the plants are small, they don't care, and as the plants get big, by the time they come to the size where they're starting to produce fruit, you're already into February and the sun is stronger and you see more growth. So what are some supplementary rules here? So it's more efficient to provide a lower amount of radiation. So that's not radiation in terms of, I'm going to die. Irradiation is sunlight over a longer time. So less light over a longer time is better for plants than a lot of light over a short time. That's a really important lesson to learn. So lower light intensity over a longer period of time will give you what's called a daily light or a light integral, right? And so you can have the same, like a brighter intense light over a shorter time that has technically the same light interval, but the plant has better use of the lower light level over a longer time. Now, it doesn't mean that you should just go buy yourself a weak little light bulb and give the crop a week, because we have to confine ourselves to the photo period. So there's a compromise, right? But generally speaking, you don't need to have a massively powerful light and then just turn it on for a short time. That's not helpful. It's more efficient. It's better, for example, to light a crop at 50 watts per square meter for 18 hours than it would be to light it with 100 for 9 hours. So that's kind of a more realistic for comparison. Although those wattages are kind of low for my example, but it was just sort of to help you follow along. But essentially, plants use light in such a way that if too much light is arriving at the leaf, the plant can't keep up. We've talked about this before, right? And if there's a lot of light, the electrons actually damage, right? That's photooxidation. But even if you're not at that damaging level, what happens is that light that's arriving is asking the plant to do something that it can't keep up with. It's like having all sorts of mail arriving at your warehouse and you don't have time to sort it. And then the next morning you're expected to deliver it, right? So the leaf falls behind. So there is an incremental benefit, right? So, and the idea is that we generally speaking, we want to extend the duration of the day, not heighten the intensity of the day, right? So we're talking about adding supplemental light to the day, so beyond the daylight. So usually lighting in the evening or morning is most effective. So not during the day so much, but more as the sun starts to go down, we turn the grow lights on, keep the plants active, don't let them slow down, to keep that growth moving into the end of the day, and then turn them off and let the plants rest. So as far as SL stands for supplemental lighting, there's typically the computer systems use sort of a threshold to decide when to turn lights on. And that may be at 100 joules per second per square meter, or 100 watts per square meter per second, ppf. You would set that in your controls. You can ask Matt about that in his class. And then, if it falls below that, then the grow lights turn on and then extend the day for that time. So looking at different crops, cucumbers and roses, they don't mind 24 hours of light. They can actually manage the sugars and shunt them to where they need to go while the light is on. So I don't know many farms that light cucumbers for 24 hours. I think that ultimately there's a cost benefit thing that you have to look at. But the point is 24 hours doesn't harm them. Tomatoes, on the other hand, should only be lit for about 16 hours. 18's already kind of pushing it. Beyond that, actually, we'll talk later, there's negative effects on the crop. So typically, and I'm saying that as an example for looking at 24-hour versus shorter times. So continuous light, otherwise known as 24-hour lighting, often has quite a few negative impacts on plants. And tomatoes, they start to get necrosis and die, leaves fall off. So typically, the grow lights then would be turned off when the sunlight reaches around 320 micromoles per square meter per second ppf. If you were thinking about watts versus micromoles, that's sort of the equivalent. So in your Priva, you would set the minimum setting for supplemental lighting. So in the morning, at a certain point, you would say, okay, the lights can come on now, and we'll run them until the sunlight reaches 320 micromoles ppf, and then it would turn the grow lights off. And then in the afternoon, when it goes below that, it would turn them back on again within the confines of your overall photo period, right? To make sure that the crop is not getting too much light. So typically, looking at April through September, the crop receives the ppf that it needs without supplemental lighting. So we don't need it through those months, which is a huge cost savings, right? Okay, so there's some studies have been done to look at supplemental lighting, bringing your overall DLI up to that 320 sort of micromole target. And that means that in the morning, when the sun is coming up, the light levels are lower, the grow lights come on. And then as you hit your target, then the grow lights turn off. And then towards the end of the day, you go below your micromole, and then you add it. So we're talking about adding 100 to 150 micromoles of supplemental. And the increases were in the order of 20% increase in yield to 36% increase in yield with the grow lights. So there's definitely a return on your investment by going up the 100 to 150 micromoles. Again, depending on your location, but for where most of these farms are located, that seems to make sense. So there is a justification for it in crops. Now, in tomatoes, when we increase the light, the overall ppf with supplemental lighting, we're increasing the sugar content, which is directly related to flavor, right? So this is where some of the criticisms come from, the flavor of hydroponics. A lot of it's genetics, but some of it's how they're grown, right? And does the farm have supplemental lighting or not? Are they allowing the plants to make that extra sugar? And on top of that, the plants are also, when they have sugar, they're able to produce other metabolites such as ascorbic acid. So vitamin C and whatnot, and the acids also contribute to the flavor. So it's a complex interplay that is, to be quite honest, is still being researched and understood, especially now in light of LEDs, because we have even more interesting outcomes that are needed to be studied. Looking specifically at tomatoes, so as far as photo period, so the length of your day, right, when the grow lights come on and when they go off, if we extend it to 14 hours, right? So remember in January we had what, 7 hours? If we go up to 14 hours with 150 micromoles of ppf, we have the largest yield and quality increase. So remember, tomatoes don't like 24-hour lighting. If you go to 17, we end up with some problems. Uh, you can get a more vigorous plant, but there is issues with sugar distribution, and also should the light come on in the middle of the night, we don't know why, but if there is interruption, you get quite a bit of necrosis forming on the tomato plants. So I think it's kind of cool that there's stuff we don't know yet, right? That's kind of cool. So yeah, 14 hours is the sweet spot for tomatoes. Um, if you extend tomatoes to 24 hours with 150 of ppf, you end up with less fruit. So you have a lower total fruit weight. They're smaller, so you have fewer fruit, and they're smaller. And you end up with lots of necrosis, and crops actually start to go, they don't shrink, but they start to die, which is just horrible. That's not going to improve your yields at all. Looking at peppers, they're a different beast. They are able to handle up to 20 hours of photo period, and the same 150 ppf, and they see typically dry weight goes up in the shoot, which means of course that there's more tissues being laid down. They're sturdy. Although if you think back to the fall with our chat with St. David's, they were saying that thinner stems are better. So that's an interesting outcome. So I see some conflicting stuff, but I'll go with St. David's because they grow pretty good crops. So they also noticed that the leaves were bigger. That is maybe good, maybe not. Hard to say. The fruit count was highest. That's good. So we had the highest yield with 20 hours, and we had the best quality. So 20 hours is the sweet spot. But where things get a little tricky, and if you remember the St. David's tour, or if you haven't watched it, you should go back and look at it. One of the issues is cost. Grow lights don't run for free. So that's where the cost for all that supplemental lighting was not seen in the increased yield in terms of revenue generated versus revenue spent for the electricity to run the lights. So that's why a lot of peppers to this day are still not lit. There's a few greenhouses that have grow lights on peppers, but not a lot. And if they do, they only have maybe a small percentage of their overall farm, and they do that so they get to market earlier, because early product gets a higher price, but demand is also sort of not always there. 24 hours of peppers, interestingly, so 24 hours had the same amount of yield as 15 to 16 hour photo period. So basically, there's no point in paying for the electricity for all those 9 hours or more that, 8 to 9 hours that you're adding. It doesn't work. You actually get decreased fruit numbers and smaller fruit size, and the leaves start to wrinkle a little bit. They don't die like tomatoes and, just poop out on you, but they do suffer. So in case you're wondering, as often I get students asking, what if we light the crops for 24 hours? Generally speaking, not a good idea. Now, what some of this stuff does is alert us to some interesting concepts, right? Why doesn't yield keep going as we increase light levels, right? You might think this is photosynthesis. We add light, we make sugar. We make more sugar, we get more growth, right? Well, it's not quite that simple, because plants make sugar for the day, and then they turn it into starch, and then they feed on that as they build and fuel their growth for the next day, and then they start the process again. But, you may have an increase in 45% of starch in your leaf after a 16-hour photo period. But at the end of the day, you go past, 18, 24 hours, you actually have a lower rate of photosynthesis, 26 to 29% less photosynthesis or less sugar production than if you had a 12-hour photo period. So more is not better. Once again, we see that, 16 hours seems to be about top. So what is it about the inability of tomato plants, to make use of that, right? Well, there's a couple of theories. about what's going on. And I'm going to tell you right now, we don't have it fully figured out. Um, the first one is source sink imbalance. Now, we've talked about source sink before, so we'll talk about that again. And the other is sugar metabolism issue. So let's start with the source sink. Um, Remember, the source is a leaf and the sink is the fruit, or essentially a sink is any growing part of the plant. So that could be apical and lateral meristems, or it could be flowers or fruit. That's been, flowers, fertilized growing fruit. So you have your leaf and you got your flower, and we're trying to move sugar from the leaf to the flower. And if you have sugar, the rate of production of sugar is exceeding what the fruit can use at that moment, then the sugars get locked up in the leaves and are less available. Or sometimes just you can form starch, and then the starch is given time, it forms hard starch crystals that are, if you are eating, for example, celery, it's very crunchy. And people often say, oh, it's crunchy because it's got lots of water. It's actually got a lot of starch, and that's the starch grittiness that's in your teeth, and that's giving you that. Potatoes, you eat an uncooked potato sometime, and you'll feel the grit in your mouth, in your teeth. That's starch crystals that are long-term storage molecules for sugar. So if we're making lots of sugar and the fruit's not getting it on time, the plant starts to stitch it into starch, which forms crystals, and then it's locked out, and the fruit doesn't get it. So that's the source sink imbalance, right? So your issue is with loading and unloading of sugars from the phloem into the fruit. It's just the speed of it's not happening. I had mentioned before, like the pre-dawn dip in temperature, where the fruit stays warmer than the leaves, and that allows the fruit to be physiologically active and steer the sugar. I had one student who sent me an interesting article questioning that theory. And for the most part, the theory is still kind of regarded as fact, but the research does show that we're not entirely sure, right? Is it because the fruit is still warm that the sugars are able to move to the tomatoes to make them sweeter? We still operate on that theory, but there is also the competing theory of sugar metabolism. So the sugar metabolism hypothesis is a bit confusing because it looks a lot like the temperature one that I was talking about, but when some scientists did some studies, they noticed if they controlled for temperature, that something similar happened. And it seems that there is some evidence that the sugar accumulation is actually related to a photoperiod more than anything. And the idea is that what they found was that these two molecules, sucrose phosphate synthase and sucrose phosphate phosphatase, they're two enzymes that you don't need to remember those, by the way, that they're responsible for processing starch to grow things, right? So, and what they found was that the plant would switch these enzymes on and off depending on photoperiods. And so by extending the day or shortening the day, they could influence the expression of these two enzymes, and that would impact the distribution of sugar. And so that it could also mean that, playing around with your photoperiod also messes up with the enzyme. So I think in truth, like most things in life, it's a bit of both. That's my opinion on it, but I thought you might find it interesting that not everything's figured out, right? So there you go. It's very similar to the temperature. Sugar is made all day, and then processed at night. And if there's not enough at nighttime, then it's not sufficiently processed and it gets stuck in the leaves. But like I said, there's a photoperiod element to that. Let's look at a farm and see what their individual practice is, kind of instead of just looking at it in terms of science and blah blah blah. This is a tomato farm in Quebec. This grower's name is Audrey Bouillon, and she works for a farm called Savora, and they grow tomatoes and they use supplemental lighting. Now, we don't call it artificial, we call it supplemental. So that's in a greenhouse. There's sunlight as well, right? It's a pretty big farm, 16 hectares, and they have 2 of those hectares have lights. So, two of them do not have lights. So most of it's lit and some are not. Now, looking at their strategy, they provide light through September. Remember, September you start to get to shorter days. So they supply light during the day and they increase the day length. So they're looking at their overall DLI going up. So typically, they're adding up to 3 to 4 hours in the morning to get 16 hours per day. So not so much at the end of the day, but in the morning. And during the day, if it goes over 250 watts per square meter, they turn the grow lights off. If it's cloudy, the lights come on. They try to keep things in the cool temperature. Now, when they get into December through to February, that's our dark month, right? We're talking Quebec. That's an even higher latitude than here. They provide supplemental lighting every day for 17 hours for their beefsteak and 18 for their specialties, which is your TOV and your cherries. That's a lot of light. That's right near the maximum of what tomatoes can handle. And they also have to deal with temperature, especially when they get towards the later part. I've often said March and April are very tricky months to grow because even though it's cool outside, it can get very hot in the greenhouse quickly. And if tomatoes get too hot, you end up with heat delay, which will reduce your yield for up to, you can compress your production for a week or two. And you can't have that. We need to have fruit coming off consistently. So when the grow lights are on, they add their own heat. And so the greenhouse is set to be more aggressive at opening its vents. So such that it takes about 30 minutes to cool by 3 to 4 degrees Celsius. So that means that the vents will open bigger and sooner, like larger gaps and sooner, to aggressively cool the greenhouse down. That's what they call a heat anticipation setting. So that the vents are moving more aggressively because of the added heat. Another really interesting practice that they do, kind of related to today's talk, but I'm going to add it anyways, is they, in all their tomatoes, they typically remove the leaf that is directly above the topmost truss in the plant. And they do that so that the sun gets more access at the growing fruit. And if this leaf is gone, the light actually comes right to the fruit and hits it directly. And that does two things. It warms it, which helps steer sugars, and it accelerates the growth because just warmer tissues grow faster. So they get larger tomatoes from that perspective. So that's interesting. So they go, when they're doing their crop management, they look at the top of the growing tip and they remove the leaf that is directly above the current flower truss. Okay. This is just a picture of their farm. They do intercrop lighting with LED with a grant they got with the government and with Philips. This is a lower crop. It's growing up and it will cover this so that plants are on either side. Intercrop lighting is a cheaper way to get light down lower into the crop. Remember when we started the lesson, we talked about light hitting the top and we needed more light because it has to filter down through all those leaves to get to the bottom of the tomatoes. Well, if you put the light in the middle, then you can illuminate the lower leaves directly without worrying about heat because it's an LED. So this is a potential real positive impact of LEDs in the vegetable industry. I think a lot of growers would be doing this right now if it wasn't because of the cost. The cost is significant. But, it's neat to see. All right. That's the end of my little talk about lighting.